Hello and welcome back to Calculus2.
Hello.
Hi. We're going to talk about sections 11.2 and 11.4 fused into a single lecture because we're talking about the properties and then the way to use the power series with those properties to do calculus. Last class, we learned about Taylor series. We learned that we can turn functions into polynomials. Today, we would like to take a look at those power series. Last time, we said that, let's say, e to the x can be written as the power series 0 to infinity of, anyone remembers? Very good. Divided by n factorial, and that one can be 1 plus x squared over 2 plus x cubed over 3 factorial, which is 6 plus ... And we also seen that keeping 3, 4, 5 terms, you are already getting an awesome precision for your calculations around where you chose, right, to center your problem. So now, the question is the radius and interval of convergence. You have to understand that power series are very tricky animals. If I give you a power series just x to the n, forget about the other fluff, just x to the n, from 0 to infinity, what would you say about the convergence of this series? First of all, which test might you consider to use to test the convergence?
Convergence? Wait, sorry, wait. Geometric. Ratio.
Geometric. We want geometric, right? Now, okay, fine, but what do we know about geometric series test?
X less than 1.
Yes. X less than, absolute x less than 1, we have convergence, and absolute x more or equal than 1, we have divergence. Wow. So technically, this series, this power series, is like a Schrodinger's cat. You don't know if the damn thing is dead or alive until you look into the box. It could be dead, it could be alive. We don't know if that system that kills the cat went off and killed it, right? So the physics says cat is dead and alive at the same time. And then the wave function will collapse to one of the two possibilities once you open the box and look at it. So this problem is convergent and divergent at the same time until you make up your mind about what is the value of x. If your value of x is 1/2, well, it's a convergent series, power series, which in that case becomes regular series, right? So far, we have three concepts, right? We have a concept of sequence, that's just an. Then you have a concept of a series, which is sum of an, sum of the sequence. And then you have the power series when you involve this x. But now, you cannot talk about convergence, divergence of the power series because it clearly depends on the value of x in some cases. In some, it doesn't. So now, this power series, as you can see, converges and diverges at the same time until you make up your mind on what the x is. But as soon as you pick that x is 3, then you don't have power series anymore, right? Because x equals 3 changes it into summation 3 to the n, and that is the good old geometric series from your chapter 10, right? So power series are tricky animals, and we can say for this particular power series, we can say that the interval of convergence is from -1 to 1. Interval of convergence is -1 to 1, and the radius of convergence is r equals to 1. Because if you see that you are centered at 0, so +1, -1 on each side, radius is 1, right? So now we would like to talk about interval and the radius of convergence and take a look at what kind of cases we can run into. Now, this is one of those rare times when I actually use examples from the book, because these examples are really awesome examples to understand the difference, right, of what we have. So we'll start with summation of x to the k divided by k n. I'm switching to, it's so much easier to write n. 0 to infinity. So we want interval and radius of convergence. Cool. Well, if I'm looking for interval of convergence, I'm looking for the values of x for which this will be a convergent series. Now we see a factorial, and that immediately screams ratio test. Exactly. So we are going to apply ratio test, and we are going to apply ratio test in 90% of these problems. The rest of the 10% is going to be the root test. Okay. So ratio and root test, but 90% of the problems will be on ratio test. So here is what's going on here. I'm going to set up my ratio. So here in blood, use ratio test. There we go. And now we have our limit, n goes to infinity. Absolute value, if you forget these absolute values, now you'll be in trouble. You'll see why. So absolute values of x to the n plus 1 over n plus 1 factorial times, and I'm immediately going to flip this so I don't have to write everything 15 times. Limit n goes to infinity. Let's peel. So we have x times x to the n, no coughing, divided by n plus 1 to the n times n factorial times n factorial divided by x to the n. Perfect. X to the n, dead. Let's go blue. Factorial n factorial, dead. And what I get now is the limit n goes to infinity of absolute x divided by n plus 1. Which variable is limit operating on? N. So x is a constant in the eyes of the limit, because the limit says n goes to infinity, I don't care about x at all, right? It's just n. So we can kick absolute x out and just have limit n goes to infinity of 1 over n plus 1, which is 0. The whole thing is one big fat 0. And now, what do we do with that? Well, 0 is always less than 1. Squeeze in less than 1 over there in red. And now we just claim that this series is convergent for every x. I'll write that in so this power series is convergent for every x. Now, the way we write that is the interval of convergence is negative infinity to positive infinity. Any value you pick for x, it will make it convergent series. Radius of convergence is r equals infinity. This is your answer, guys. That's your answer. This power series is convergent for every x. So interval of convergence is negative infinity to positive infinity, and radius of convergence is r equals infinity. Okay, cool. Next example is my favorite out of three. Summation -1 to the n, x minus 2 to the n divided by 4 to the n from 0 to infinity. Exam grade question. You gotta start this one. Like, easily. Exam grade question. Either exam 3 or the final or both. A staple example. All right, cool. What did we say? Ratio test, right? Ratio test has that absolute value that will kill the -1 to the n. So we don't need to bother with anything else. Yes?
Okay, I think you just answered my question.
I did, because you wanted to ask about alternating series.
Yeah.
I could see it in your eyes. One eye was burning alternating, the other one was burning series. And as soon as I said absolute value will kill -1 to the end, he was like, God damn it. And the fire was no more.
It was thunder, not fire.
Oh, okay, yes, all right. Yeah. Thunder, all right, fine. So, oh, you shouldn't have, thank you. So, we are going to look at... Is it birthday?
Oh no.
Oh, just checking. I make everyone sing. So we are going to do ratio test on this one, and if you forget absolute values, the problem is immediately going to be garbage. So you must use absolute values. Now let's go and do the same thing. Absolute values will kill -1 to the n, so I'm not going to bother. Limit n goes to infinity, absolute values. I'm immediately going to peel off x minus 2, have x minus 2 to the n, divided by 4 times 4 to the n. So I already peeled +1, because that's why I have doubles there. If you put them together, you will get your n plus 1s. Times the problem flipped, so 4 to the n divided by x minus 2 to the n. And now we have these guys to cancel and these guys to cancel. And when you look at the remainder of the problem, you have your absolute value of x minus 2 divided by 4. Is there an n?
No.
So is there anything that limit can do? No. Right? So we just kill the limit. The limit has nothing to operate on because there are no n's. And we got this. Absolute values are still there. Now, remember what we are looking for. We are looking for convergence. So what do I get to add in there? When is the ratio test convergent?
It's less than.
When there is less than 1. So you want the convergence, which is why you put this in. And now you have to solve this, what we call triple inequality. And this is where, right, your problem dies if you don't have absolute values. You have to solve now absolute value x minus 2 over 4 less than 1. And the meaning of that in algebra is negative 1 less than x minus 2 over 4 less than 1. You would lose this side if you don't have absolute values. That's why they're not optional. So now multiply everywhere by 4. So times 4 first. You get your negative 4 less than x minus 2 less than 4. And now add 2. So multiply all, add all. And you will get your negative 2 less than x less than 6. You see, you got your interval of convergence. Again, if you don't have absolute values, all of this is gone, and you would not be able to write your interval of convergence negative 2 to 6. You will just have a 6. You will not have negative 2, right? So make sure you have those absolute values for both ratio and root test there. Cool. And I have my interval, so that's the interval of convergence. What's the radius equal to? 4. Why is the radius equal to 4? Because let's draw this. If I have my interval of convergence here at negative 2, and then it ends at 6, the middle is 2, because you have 4 units here and the 4 units here. So radius is 4. Now, looking at this diagram, right? Do you guys see something interesting looking at a problem as well? I'll draw the diagram again and then erase it. Well, that's why it's radius, right? So you add 6 units on one side, 2 units on the other side. When you add them, it's 8, right? So radius is half of that. Yes? Okay, that's a nice thing to see. 4 is in the denominator. Cool. That's not what I'm looking for, though. Looking for something we talked about last class, and now it's obvious also. Yes? Yeah, how do we call that? Yes. Do we all see centered at 2? That is going to be your checkpoint at the end of the problem. All right? If you had x minus 7 and you get the interval of convergence to be, 3 to 6, your interval doesn't include the centered point, so that's a problem, right? They must be centered at the same. So when you calculate your interval of convergence and you get all the way down, if the problem was centered at 2, x minus 2, problem can be centered at negative 5, x plus 5, right? Then it's centered at negative 5. So it has to be in the middle of your interval. And that's how you know that you did it correctly. So right now, over here, I'll just write in blood, x minus 2 centered at x equals 2. So you will remember that when you look at the notes again. All right, so what did we find for this problem? We found that if you pick an x anywhere between a negative 2 and 6, So you can pick pi, it's okay. You will have a convergent series. If you pick anything outside of this range, you will have a divergent series. And radius of convergence is there, right, to see one side, other side, and also show the center, which is where the whole series is centered. Cool. So the first problem converged for every x under the sun or outside the galaxy. The second problem converges only with numbers between -2 and +6, not including those, right? And now we have the third problem, summation 1 to infinity of n times x to the n. N factorial times x to the n. Ready for ratio? Limit n goes to infinity, absolute values, n plus 1 peel off n factorial x times x to the n divided by original problem, n factorial x to the n. Close absolute values. Cancel factorials, cancel x to the n, and what we get is kick x in front of the limit, and then have limit n goes to infinity of n plus 1. Now what's that? That's going to be x times infinity, right? Is greater than 1. Unless x is 0. Nice. So yeah, this is going to diverge everywhere except if x is equal to 0. So you pick any number, you get yourself divergent series, you pick x equals 0, it converges for 1 point. So we will write this series, this power series, converges for x equals 0. That's it. So you don't have the interval here. Your radius of convergence is 0 because it converges at a single point. So now we have a problem that converged for every value of x, problem that converged for some values of x, which was the middle one, and now this one which converged for a single value of x. If x is 0, the problem will converge. Now why would that converge? Because anything multiplied by 0 goes down into a 0, right? And the sum would be 0. So these are the problems that you will work with. These 3 examples covered all 3 possibilities you guys can have. And I also gave you an example up there when I introduced the concept using geometric series, where we considered why we're doing all of these things. I'm going to mention, for those of you that are wondering why are we using the word radius when there are no circles anywhere. Well, the world doesn't end with Taylor series and right, there are also Fourier series, Lorentz series, and so on. The term is actually from the complex Lorentz series, where you have I'm going to erase this. You have your real axis and imaginary axis, and then you have your series, in there. You find the radius of convergence around the whole series, right? And that's going to be your radius. Now, obviously, as soon as I get rid of the complex domain, the whole thing still stays as a radius, but it's just a length on one side. So that's the reason why we call it radius of convergence. It's also nicer than call it something like half interval or whatever. And the reason why we're looking at the radius of convergence is to see also where the center is, right? Because you want to be at the center. So those are the first two properties that we are considering. One is called interval of convergence, and the next one is called radius of convergence. So now we're going to take a look at convergence. We're going to take a look at the properties of power series in terms of combining power series. Now, this is still 11.2, but it's the intro into 11.4. This is where they bridge. So, suppose that summation Cn x to the n converges to f of x, and summation dn x to the n converges to g of x. So these are the two conditions. Now we have number one, sum and difference. We'll say that the power series of Cn x to the n plus or minus dn x to the n is going to give you f of x plus minus g of x. It's one of the linear properties, which is awesome to have. So if you have multiple series added, this tells you that you can split them into separate series and deal with them individually. Now, obviously, if one of those diverges, it ruins it for everyone, right? Number two, multiplication by a power. Those of you going to differential equations, star that one, because you are going to see it in both of these you're going to see in DFQ, but number two in particular. And this one says that if you have some x to the m in front of your series Cn x to the n, you can pull that x to the m inside and combine it with the n you had over there. Euler's equation and so on for differential equations. Number three, the one that it's important for 11.4 and where 11.4 begins, is function composition. Function composition, and this one allows you to have summation of Cn and then some kind of function h of x to the n. Remember that summation Cn x to the n is already a function, and now you're replacing the x with another function. So that's called function composition. So number one is good everywhere. Number two is going to be for differential equations. Number three is going to be for this class. It's going to be included somewhere. Probably in the final with one of the integration questions. I think. Okay. So now from here we can transition into the calculus of. This is now where 11.4 technically starts, but what I'm going to write is in 11.2, so it makes no sense, but So derivative and integral of power series. Now we understand that the power series can turn stuff into a polynomial, and then you just go from there. But what I want to write here is the derivative of the actual power series. And we have that suppose that summation Cn x minus a to the n, right, infinity, converges to f of x. So what is the f prime of x in this case? It will be summation of, and now you're supposed to take the derivative. You know that Cn is a constant, so you get to copy Cn. But then when you do the derivative here, you get your n, you get your x minus a, and you get your n minus 1 on top. Now, it doesn't show in a book, but this is the key point. 0, 1. When you take the derivative, write this in blood if you're going to differential equations. Every problem will have it. When you differentiate, a power series counter moves by 1. That means when you are in a second derivative, it moves by 2. If your original problem is starting at 7, then this one's going to start at 8. And why is that so? Well, remember what derivatives do. They kill the constant term. Is your power series the first term was a0 or c0, and then the next term was c1x, right? Okay. That term is killed right there, which messes up. Now, if you want to do the theory and all that stuff, right, it's not an honors section of the class, so we don't go into the details. I just want you to know that, because those of you taking DFQs, maybe even next semester, I don't want you going why, because I told you why now. With the second derivative, then you would have n minus 1 drops down, Cn x to the a, and then n minus 2. You can keep taking these derivatives regular way. I forgot the word then. So suppose that the power series converges to f of x, then the derivative of f of x is this, when you just differentiate. And what did I differentiate here? I just differentiated this. This is like x squared, right? You put 2 in front, and then you have minus 1, which is 2 minus 1 will be 1, right? So it's basic derivative. And we have also integration, which we are not going to use in differential equations. Integral of f of x dx would be summation ck x minus a to the n plus cn divided by n plus 1 plus c. Integral keeps the same because everything shifts by 1, and then you lost your constant term, but you have a plus c added, so it's right back in. So integral remains on the 0 and keeps the infinity up there. Again, we're not going to use it in differential equations, but you might have a problem in Calc 2 final to use it. So there we go. These go on the cloud. And why we love them? Well, this is, again, it was in 11.2, but technically part of 11.4. So here we go. I want to know what is the integral of e to the x squared dx. There is no technique that you can use in Calc2 to solve this, right? You need that square gone to be a basic integral. You need x in front of e to be a basic u sub, right? Integration by parts doesn't work either, no matter what you pick for your u and dv. So all of the methods fail. You can't use trig sub, obviously, and you can't use partial fraction decomposition. It's not a polynomial. So there's nothing that we can do. There is something you can do in Calc3, but then that's Calc3, right? So what should I do? Well, the first thing I wrote when we started a class is that e to the x is 1 plus x squared over 2 plus x cubed over 6 plus dot, dot, dot. That was the first thing I wrote, right? When we started a class. And then I had this property which allows me to have function composition. So now every x will be replaced by x squared, because that's how you achieve function composition to build e to the x squared, right? To build e to the x squared, start with e to the x, then replace x with orange, x squared. So, and then you get your e to the x squared. So now do we see that all I need to do is to write e to the x squared instead of x will be 1 plus, and now you're replacing it with x squared. Oh, I'm going to regret this orange. Plus replacing every x with x squared. That gives me that e to the x squared is equal to 1 plus x squared plus x to the 4th over 2 plus x to the 6th over 6 plus dot, dot, dot going on. Integrate e to the x squared dx is about the same as integrating 1 plus x squared plus x to the 4 over 2 plus, let's say, x to the 6 over 6. Cut it there, right? Cut. And now you're integrating a polynomial. Holy nightmare, this is such an awesome thing, right? We went from something that can't be integrated, not unless you know the trick from Calc3. We went from something that can't be integrated into something that we're just integrating a polynomial. The story changes a little bit if you have the limits and you have to worry about the precision and all of these things. Then you have to figure out where to center your power series. But in this case, the power series is just centered at 0 because I gave no parameters of any kind for this. So it can be used, right, in these situations when you run into something that you can't integrate. You use power series, if you know the power series, obviously, to deal with that. I think I ran out of things to say. We can differentiate, since we didn't do any differential problems. Let's differentiate sine x. Now someone would just say, derivative sine is cosine, and move on. You're 100% correct. However, right, for the purposes of upcoming holiday, right, let's expand the sign, right, so we can have a conversation rather than just, cut it abruptly. It's cosine x and walk away. Like, way to be smug, right? Share the knowledge. So what do we have for sine? We have x minus x cubed over 3 factorial plus x to the 5 over 5 factorial minus x to the 7 over 7 factorial plus x to the 9 and then 11 and then 13. So we are differentiating this polynomial whose derivative is 1 minus 3x squared over 3 factorial plus 5x to the 4th over 5 factorial minus 7x to the 6 over 7 factorial plus dot 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 going on forever. This is equal to 1 plus x squared over 2 factorial because 3 canceled. 5 and 5 now cancel. You get x to the 4 over 4 factorial. Minus 7 and 7 cancel. We get x to the 6 over 6 factorial plus dot dot dot.
The first sign should be minus sign.
That's what I have. Please pay attention. Thank you. So now this condenses into summation negative 1 to the, well, we'll start at 0, go to infinity. If I'm starting at 0, the first one is positive. And then I have x to the 2n divided by 2n factorial, and that is cosine x. So derivative of sine is cosine. At one point I asked students to compute the derivative of cosine using power series. You know that your target answer is negative sine because you know your derivatives. But then to just grind through this calculation using 4 or 5 terms, where is that minus coming from? And you can, if this is your cosine expansion, you see where the minus is coming from, right? Because when you take the derivative of 1, we get x squared. When you take the derivative of 1, you get 0. And you see how your first term is negative, right? Because the next derivative would be 2x divided by 2, which is just x, but it's negative x. And it's opposite of what sine? Sine is positive x. Yeah, you can keep taking derivatives. You go sine, cosine, negative cosine, sine, cosine, negative cosine. And they flip around like that. There's so much cool stuff, guys, with this. And it's going to be used a lot with electrical engineering, signal processing as well, and so on. Some of the computer science, more advanced stuff, will definitely go back to this. But the main concern of you right now is your differential equation, chapter 3, where you are going to use these. And you are going to use them with shifting the counter. Shifting the counter is something that you learned in geometric series, to shift the counter back to 0 so you can use your sum formula. And in differential equations, you will have to shift the counter because you have to combine the sums together into a one sum. They have to start at the same number, and they have to have the same x to the n exponent, otherwise you are doomed. So shifting the counter here works exactly the same as shifting the counter anywhere else. So if I have a power series that I differentiated, then I just need to shift the counter back to bring it to, let's say, a common 0 or something. So let's say you have the derivative of summation 0 to infinity of I don't know, x minus 3 to the n divided by 2 to the n. So to differentiate this, you make all of this into a single exponent problem. So summation 0 to infinity, and they mush all of this together, everything raised to the n. So now when you take the derivative, still have your summation, and now starts at 1. Let me put that in blood over here. And then you have your n times x minus 3 over 2 to the n minus 1 because you differentiated. You went the power down. Now, need to shift the counter. Need to shift the counter, and we know that this is n equals, right? So I'm going to subtract 1 on both sides. Absolutely same steps we did in geometric. Subtract 1 on both sides, we get n minus 1 is equal to 0. Call this m or k or whatever. M equals 0. So from here we figured out that m is n minus 1 or n is m plus 1, depending on what we need to plug in. So now we have summation. M goes from 0 to infinity. Now we have n. We don't like the n, so it's n plus 1. And then you have x minus 3 over 2. And then your n minus 1 is just m. Now, here is the thing that bothered the living hell out of me when it was introduced for the first time in differential equations. Professor just said, okay, we are done. Rename it, and wrote summation n goes from 0 to infinity, n plus 1, x minus 3 over 2. I screamed, you can't do that! And he said, yeah, I can. I wanted to cry because the substitution was, right? M and n are off by 1, and for renaming it, just swap the letters. Damn thing works, actually. So yeah, that will be a weird step, whenever you take differential equations. But once you shift the counter, you can rename your variable to whatever you want, because all of the dynamics between the variables actually already work their course out. So then you can call it whatever you want. So shifting the counter for power series works exactly the same as shifting the counter you learned in geometric. Now we are not going to need this for Calc2, any of the exams. What you see on the screen right now, you're not going to need it in this class, but differential equations, every problem will have it. And you'll have to do it twice because you will use this for the second derivative equations. So there will be a second derivative there, which means that counter starts at 2. So you have to do one shifting the counter for the first derivative, and then one more for the second derivative, and then when they're all the same, combine them together, get the recursion, solve the problem, go through it. It's just about 40 minutes, not a big deal. Easy. That's it. Turn your function into a polynomial and then just integrate. Integrate the polynomial. Oh, I didn't tell you about the yeah. Okay, so you have to be careful if you have definite integrals. That is insanely important. Let's say that you don't want to solve the integral e to the x sine x dx from 3 to, let's say, 3.1. And you don't want to go through the whole procedure. Can anyone tell me what is insanely important as you are working on power series for this problem? We know the power series for E, keep 3 terms. You know the power series for sine, keep 3 terms. you know you're going to multiply them all together, get the long polynomial, and then you integrate term by term. What might be very important for those power series? Not what might be. What is very important for the power series?
What's the factorial of 3.1?
I'm sure you're within raise.
The what?
You're within radius.
Well, yes, we will be working in radians, yes. Would this problem be handled differently than this problem? And what might be the difference?
Is that the center?
Yes.
Center.
The first problem must be centered at 3. The second problem must be centered at, let's say, 12. If you don't center your power series around the limits that you have, you'll be working on the numbers that have nothing to do with your values. So this problem must center at x equals 3, must center at x equals, let's say, 12. You can center at 12.5 or whatever. Right? But it has to be centered in that neighborhood. You cannot use your vanilla e to the x and sine x from the chart. Because, I mean, you do use them, you just put minus 3, right, for x minus 3. Because, remember the graphs, right? The first 3 terms snaked around. But remember, we had to use 3 terms just to make sine x match up to pi over 2. Now, where is 3? Right? 3 is at pi. But at that point, they were already apart a lot. So if you replace that has maybe 20 points separation on the y, all of your numbers will be terribly wrong. So you must center your power series around limits and then go through calculation, which makes definite integrals tricky because you have to remember that part. So now this power series here would be 1 plus x minus 3 plus x minus 3 squared over 2 for e. On the other side, for sine, it's going to be x minus 3 minus x minus 3 cubed over 6 plus x minus 3 to the 5th over 120. And then you have 3 terms and 3 terms. You FOIL, and then again, all of these things, guys, is 200 years old. There were no calculators, computers. Today, what do? You whip out your cell phone, you push a few buttons, and the damn thing is integrated. Yes?
So you're just changing x to x minus 3.
Yes.
Okay.
Which is why it's beneficial to memorize those power series from the chart, right?
Yeah.
I mean, they will come in handy in differential equations, but not everyone goes to differential equations. It's okay, right? You don't have to memorize them, but it's very beneficial if you do. And I said those 5, sine, cosine, and then 2 hyperbolics, which are the same minus alternation and e, right? You get those and you're good to go. Cool. Bye.